So the theory of the experiment is sort of interesting. Now you'd argue that you pull this back to a certain set distance, that this energy is the same no matter what you do. Okay, you're going to produce the energy from the spring. But the catch is...
So you do understand that the energy is coming from the spring. That's what's powering the system.
The faster the whole lever moves, that means the more you have to subtract for the lever, okay?
Right, why are you talking about the faster the lever moves? The whole argument you've had is that the lever will move at the same speed when the masses are placed individually at the respective locations.
It's going to consume some amount of the energy. So the faster the whole lever moves, the more energy it's using.
But again, why are you arguing that now? Because the whole premise of using this lever was that, unlike the spring, it's in contact and the spring gives the same energy to the masses and they move the same velocity according to you.
Because the velocity, and the slower it moves, the less energy it's taking from the experiment. So these are, you could argue, ideal locations where you obey the law of the lever.
Yes, and you want to change those locations now because it's not going to come out your way.
But if you disobey it, you'll get close to the same results, okay? Not the same, because you're losing or gaining energy by how much you've given to the lever.
But again, you're now saying that there's losses of energy to the lever, but the whole argument you've had in using the lever is that it combats that problem.
But for example, if I did put the one mass at the same location as the two mass, it's still going to go substantially faster. It's just not going to go twice as fast.
So substantially faster, is that a figure? And you're conceding that it's not going to go twice as fast. So it's got half the inertial mass, it's got half the rotational mass, yet it's still not going to achieve twice the velocity because the lever would have to move twice as fast, and it won't.
Because the lever itself will be going much faster to be able to release its energy into the object, the whole...
So now it's much like the spring argument, isn't it? Now it can't get all its energy in, that's why it doesn't go twice as fast. Nothing to do with the conservation of energy, and that's why it doesn't go twice as fast.
Lever will have to go much faster to increase the velocity of the one mass. And if I put it out a little further, then we get into...
So why would you put it out further? The old argument has, again, been placing them at the correct points, like the balance lever. Now you want to change the goalposts.
An argument, again, about how, it'll be much better. So the further out I put it, ideally speaking, I'm making the lever...
The further out you put it, the more inertial rotation you're going to give it.
Move less, so I should be able to get even more velocity, a little bit more. So instead of being too close in...
So you say.
You want to be too far out. So if you're going to make an error in your measurement, you want to make sure your error's out, not in, for the light mass.
So again, you want to change the positions to try and work it to your advantage, which ain't going to happen.
And in and not out for the heavy mass, because that'll change how much energy the lever has to steal.
So again, why now is suddenly the lever stealing energy when the whole argument of using the lever was it was to combat that problem as opposed to just launching off a spring?